Quantum Mechanics, the Riddle of Internal Motion in Experiment and Theory, recently published. It's up. I'm going to describe data that is extensive and irrefutable, data on wavelength and frequency and millions of measurements, based on plane waves, where the wave is a ripple, it's forced with wavelength lambda, and if you take a point on the ripple, it bobs up and down with frequency f. Then what is the velocity of the wave? The velocity is the wavelength times the frequency. That's fundamental. The trouble is, the riddle, de Broglie's hypothesis, makes the velocity inversely proportional to the wavelength. So what is quantum mechanics about? I'm going to start with the data. This is a table used for making measurements in an electron microscope. We need to know the energy of the probe, which is measured, and calculate the wavelength of the electron probe, the mass of the electron, the velocity of the electron, the frequency of the electron. And there are ways of calculating these, and the many millions of consistent results make the data and the methods irrefutable. So what are we talking about? Internal motion. Dirac wrote, in the theory of the electron, we shall have to introduce an extra degree of freedom describing internal motion. The trouble is, he said almost nothing about it. But we describe it in the wave packet, which we're going to compare with Schrödinger's theory and Heisenberg's theory. Schrödinger's theory allows us to calculate eigenstates of a Hamiltonian matrix equation, and it's non-relativistic, partly because the mass energy is neglected as if it's unchanging. But this method is very convenient for chemical calculations. Heisenberg's interpretation is, by contrast, relativistic. It's distinctively mathematical, using Poisson brackets, commutators, the uncertainty principle. For example, Dirac calculated the speed of an electron by means of this Hermitian operator and found that it is equal to c. He wrote, this means an altogether different relation between velocity and momentum from what one has in classical mechanics. We can conclude that a measurement of a component of a velocity of a free electron is certain to lead to the result plus or minus c. How this can be allowed by special relativity, I don't understand. But Heisenberg's interpretation is indeterminate and discontinuous. It requires spooky action at distance, and it has no wave packet. By contrast, the wave packet has relativistic internal motion. It fills gaps in former theories. Its quantum depends on harmonic states at creation, annihilation, and transmission. Measurement is real with wave particle, temporal and spatial uncertainty. Well, let's proceed to wave particle duality. Here's the wave packet. It begins with Norton's corpuscles, which are travel in straight lines like inertial mass, and modified by wave mechanics of the 18th and 19th century, including Maxwell's electromagnetism, which seemed to make the theory of light complete at the end of the century, until the quantum was discovered. With Planck's law and de Broglie's hypothesis, special relativity. In simplified units, we find that an equation for mass squared is angular frequency squared minus wave vector squared. And this separates into two parts. A conservative part describing mass, charge, spin, energy, momentum, the envelope, and an interference part describing interference, superposition, creation, annihilation, entangled and resonance, described by an infinite wave with amplitude 1 for all x and t. X is a combined variable. Since A normalizes phi, phi is quantized. We can operate on these equations in many ways. For example, by the Fourier transform. Noticing that omega bar and k bar are mean values of varying functions. From the figure we find that when x equals 0, uncertainty in time is 2 sigma. The Fourier transform of the Gaussian is Gaussian, so we can get an equation for the distribution of angular frequency, and normalizing the argument, we find the uncertainty in angular frequency is 4 over sigma, multiplying sigma cancels, d omega by t equals 8, dkx by dx equals 8. This is slightly larger than Heisenberg's limit. I'll say one point about the limit. We have limits when a lambda by 2 is equal to 2 sigma. There's a cutoff. But that's all I would say for the moment for limits. We go on to differentiate this equation, which has a very important result. The differential of these constants is 0. The differential of this equation gives us omega over k times d omega over dk is equal to c squared. Omega over k is the same of frequency times wavelength. It's the phase velocity of the wave. And d omega by dk is similar to the beat velocity of a loaded tuning fork. And that is equal to the group velocity. So the product of the group velocity is equal to c squared. Light is a special case. When m equals 0, vg equals vp, the group velocity and the phase velocity are equal. For the electron, where m is greater than 0, the group phase velocity is the inverse of the group velocity. The phase velocity is greater than c. The group velocity is less than c. And so we can calculate lambda and f for the electron probe in an electron microscope using Pythagoras' theorem operating on the equation for special relativity. The mass energy is given by the vertical green vector. The electron probe energy is equal to the mass energy plus the acceleration energy. And joining the vectors, we have the kinetic energy of the probe electron. From these we can calculate the frequency and the wavelength. This formula is the same as this formula. And what is the result? Here's a table showing acceleration energy, frequency, wavelength, phase velocity, group velocity, product of group velocity, phase velocity equal to 1, and the ratios. Here they are plotted with the accelerating voltage plotted along the horizontal axis. The frequency of the electron is about 10 to the power of 20 cycles per second. Its wavelength is about an angstrom. Multiplying these two, we get the phase velocity. The mass energy of an electron is about 500 kilovolts, and that separates the relativistic behavior from the non-relativistic behavior. The phase velocity is the product of the frequency and wavelength, and that is greater than c. The group velocity is the inverse of that. It's given by relativity. And it is less than c and tends to 0 at a very long wavelength. the product of the phase velocity and group velocity is equal to the constant 1. And the ratio is 1 in the relativistic range, but increasing in the non-relativistic range. And we can begin to sum up. The riddle is solved. Broglie's velocity is the group velocity. The phase velocity that we examined in the first slide is the product of frequency times wavelength. The phase velocity is the inverse of de Broglie's group velocity. Finally, a comparison for the bound electron. This calculation was for a free electron. When an electron is bound, its energy is less than its rest mass energy because of the Coulomb binding. And a typical binding energy for a ground state is half the mean Coulomb energy and equal to the kinetic energy. So this is how these calculations can be made for a bound state. And we can conclude. Phase velocity of an electron that is accelerated to 10 electron volts is 10,000 times its group velocity. Matter cannot travel faster than the speed of light, but the phase velocity of the electron does within the wave packet. There are consequences. In measurement, instantaneous discontinuities are unnecessary in the reduction of wave packets. There are consequences for intrinsic spin, antiparticles, Newton's second law, the Hall effect, etc., and possibly new implications for gravity.